Desser and Misner. And the problem with that formalism is was not very clear the general covariance, because essentially the canonical formalism takes time from the very beginning as a special coordinate. The second problem was that there were, in the calculations, a lot of divergences. And it's very hard to handle the divergences in a canonical formalism in a consistent way that preserves Lorentz and Poincaré symmetry. Then, in the second lecture, we were dealing with the covariant approach, which in principle for field theory proved to be equivalent to the canonical one, but the advantage is that in this formalism, the normalization is much more accurate and safe. In fact, historically, in field theory, the field theory started to be formulated the day after quantum mechanics was formulated. So in less than 1 year, the people were willing to quantize fields, especially the electromagnetic field. Just to explain the transitions into atoms, you need to have also quantum theory for photons. And this is why they were interested. But it took almost 30 years to solve the problems of the divergences of quantum electrodynamics. And this problem was solved in the covariant formalism. The first steps in quantum field theory were in the canonical formalism. But then, solution to the handling the divergences was done in the covariant formalism. The same, this is why here we have these two separate blocks, even for quantum gravity. First, you understand the quantization in the canonical formalism because it's more intuitive, it's more linked to the standard approach to quantum mechanics. But we learned that dealing with divergences and trying to preserve maximally the covariance of the theory is a good point. So this is why the covariant formalism, which we formulate yesterday, was more appropriate. But none of the formalism can hide that there are fundamental problems. No matter which formalism you use, there are fundamental problems. The fundamental problem is that this theory is non-renormalizable, both in the canonical and both in the covariant. I think yesterday you have some glimpses why this is so. There are not too many calculations. I refer you to papers, but not to the, I did no calculations because a shortage of time does not allow to do that, no? But the essential point is that the theory is non-renormalizable. So in the covariant formalism, it was natural to suggest that perhaps we could arrange the situation by going to higher derivatives. But then we realized that there was a problem. Because if you quantize these theories with higher derivatives in the covariant formalism, you don't know how to go to the canonical formalism. So maybe we lose the way. And the reason why we cannot go to the canonical formalism is that perhaps because we are losing some fundamental principles of the quantum theory. And today we will come back to these fundamental principles and try to understand if the problems which appear in the higher derivative formalism are important or they can be handled in some way. This is another perspective of the problem which was addressed in the lectures by Gabriel for the Leawick theory. So let's come back to the fundamental principles of quantum field theory. I will be not very precise. I just describe some of the principles. There are more that should be preserved, but anyhow, it's important. One is Poincaré invariance. Let's think in standard quantum field theory. Poincare invariance. In general relativity, we have more than that, no? But Poincare invariance, we should preserve. It's a relativistic theory. So we have to have Poincare invariance, which means that in the Hilbert space approach, there should be a representation of the generators of the Poincare transformations, at least at the fixed time transformation. It's hard to explain in the fixed time formalism how the boosts are presented, but it can be done, so believe me. So the second principle, which is very important, is microcausality. Microcausality, I told you, for scalar field theories was... So this is field theory. Apart from Poincare invariance, there should be one main actor in this game, which is the operator called field. Everything depends on what is the quantization of the field. So apart from Poincare invariance, you have a main actor, which is the main character, which is the operator associated to the field. This field is local, so it depends on why. Well, in fact, this is quite singular, but so this is the microcausality. It's a fundamental principle because it tells you that if you make an operation in the point y at a given time, and you perform another manipulation on the same field in point x at the same time, they should be independent. What I do here, nobody knows there because they cannot communicate by a light signal. So this is a fundamental principle. There are things you can do separately. They are mutually commuting operators at fixed time. But in the covariant formalism, because you have Poincare invariance, you cannot always stay at the same time. You can have different times, but nevertheless, this is zero whenever there is no causal connection. This is why it's called causality, microcausality. Okay? This is what is there. Another principle is that the vacuum should be stable. Otherwise, we will not call it vacuum. So in most of the theories, everything starts with the vacuum. This is different than in quantum mechanics. In quantum mechanics, for instance, hydrogen atom, there is no vacuum because there is an infinite tower of energy levels which go down to infinity. So negative energy. So there, the existence of vacuum is not important. But in quantum field theory, it's fundamental. This is one specific property of quantum field theory. Quantization of the field, microcausality, and stability of the vacuum. And then we add renormalizability. Although we have seen that in the last years, this condition has been relaxed in effective field theories, but from the fundamental viewpoint, it's still a conceptual requirement, because otherwise you have to change at any time the data you need to fit the predictions. Depends on the order of perturbation you are computing, so it's very unpleasant. So the standard consistent quantum field theories require a finite number of parameters, and once you fix that, the rest are predictions. Well, let's, for a while, stay strict in this sense. This is why we move to higher derivatives, because otherwise, even Einstein relativity could be quantum field theory. You don't worry about the fact that you generate new interactions. If you don't care about that, this will be. So, from these principles and some others, which are technical and not written in the slide, you can prove that you can extend your fields to points which are in the complex plane of the time coordinate. You can prove using the principles. And in particular, you can extend the definition of these field operators to a larger domain in the complex plane of time, which includes the pure imaginary time line. So by analytic extension of this field, you can extend the operator to values where the physical time becomes imaginary. And this is the basis for the Euclidean formalism. If you, instead of looking at the fields in Minkowski, like here, you meet at the analytic extension of these operators to the pure imaginary time, you formulate Euclidean version of the quantum field theory. So your operator now is well defined there. In fact, it turns out that it's more regular because these operators are not, this is the technical part which is hidden there, are not well-defined operators because the dependence on X is very poor. I mean, they are in fact distribution, operator-valued distribution functions. To be well-defined, better, you smooth the operator with some external test function, a wave packet, let's say. And this is a well-defined operator now, depending on the function f2, not x, just f. But it turns out that these operators here are still very wide. If you restrict to the imaginary part, the equivalent version of this is much more regular. Only if you have two operators which collide on the same point, you have a singularity in the correlators here. Otherwise, you have a function. Schwinger functions, which are the correlators of these guys, are functions. Whereas the Wyman functions, what people call Wyman functions, which are correlators of these operators, are distributions, not functions. Even if they are not at the same point, they are distributions. Okay, this is a technical problem, but since we are talking about principles, let's be more specific. In the implications of this stability of the vacuum and so on is implicit. You can, that there cannot be unphysical ghost operators. Why? Well, the question is, who is afraid of ghosts? Well, the ghosts imply an instability of the vacuum, generally speaking. But some of the ghosts are not that bad, as you see. The Holy Ghost is somebody very popular in Catholic countries, right? And this is a good ghost, let's say. But there are also other good ghosts, which are like the Faddeev-Popov ghost, because they are necessary to quantize the theory in the covariant formalism without suffering. If you, in the canonical formalism, you never have ghost, because you don't start with a theory where you have ghost. But in the covariant formalism, you have too many degrees of freedom. You remember yesterday there was a counting, and to kill the degrees of freedom, the best way was just introducing ghosts which were eating degrees of freedom. Each ghost eats 2 degrees of freedom. The vector field, you have 4 degrees of freedom. You have a 1 Faddeev-Popov ghost, which transforms 4 in 2. So it's 2. In gravity, the same. In gravity, you have 10 degrees of freedom. You have 1 vector ghost. That means 4. 2 times 4 is 8. 10 minus 8 is 2. So this way of counting with ghosts is simpler than just proceeding by gauge fixing and so on. But there are bad ghosts. And we have seen yesterday some of them in the formulation of quantum gravity. We have, for higher derivative, the quadratic gravity formulated by Estelle, we were discussing these two propagators. The two-point function has two pieces. One is this, the other one. And both of them have, apart from the graviton and one good ghost, one kind of Faddeev-Popov ghost, you have, which is essentially, here is absent because there is a misprint. There should be extra p squared here in the denominator. Sorry. Oh, I thought that I have corrected this. Maybe it's not the right file. Let's see. Yeah, I replaced the file this morning, and this is not the right one. So, okay, but the correction is that there is an I here, and an extra p squared in the denominator. Okay, this 1 over p squared, which is in both cases, is just, in the first case, the graviton, in the second case, the Faddeev-Popov ghost of the graviton. But there are other ghosts, because you have here another poles and here too, okay? Well, here's the version we have plotted yesterday for the projection operators of helicity 2 and helicity 0 in this case of quadratic gravity. So let's try to see why these ghosts are compulsory, what they should appear in these high derivative theories. Reason is a topological reason. If they are real, imagine a polynomial theory. You see here in the denominators of the propagators, you have a polynomial, which is quartic here. And here is also quartic, but is not explicitly seen because there is a p squared missing factor. It happens that when you have a polynomial with real zeros, the poles are the zeros of the denominator, well, you have this picture. So a polynomial with real zeros is of this type. If you assume that at infinity you have a leading term which is positive, so it's an even polynomial of p, so this always grows at both ends. But each time you have a cut here, you have another zero in the next point. If the slope is negative, this one is positive, and so on. They are alternating signs. So it means that when you make this single fraction, the composition of the polynomial of the propagator, scalar propagator, is the inverse of this. You have alternating signs of an, coefficients in each of these propagators, which means that you have alternating ghost, because minus sign in this propagator means that it's the propagator of a ghost. So it's unavoidable to have ghost if you have a polynomial which has more than two zeros, or than one zero. So in polynomial higher derivative theories is unavoidable, the fact that you have ghosts. So in this case, where all the zeros are real, you can try to extend the Feynman prescription just to find the right propagator. And we do it in real time. And, well, if you do it in a Euclidean time, this will be the imaginary part of the complex plane of zero component of the momentum. But then, so if you do this way, you can perform a weak rotation and go to the vertical axis. So it is possible to go to Euclidean time, as I was derived in normal theories from general principle. Here we cannot use that because we don't know what are the fundamental principles of these theories. But this, what happens is that in this case, there is no reflection positivity, because a consequence of the principles I was mentioned at the beginning is that the correlators should satisfy a property which is known reflection positivity, which was discovered by Osterwalder-Rader. This property, I mean, is quite complicated to describe in short time, but let me just see one piece of that. Reflection positivity means that if you have, in this scalar case, a function f here, complex, and the same function at point y, and here you have the Euclidean analytic extension of the two propagators, of the two-point propagator, this is why reflection positivity has two effects. One, reverse the sign of the Euclidean time, and the other one, conjugate the function which is on the left. Reflection positivity means that this integral should be 0 for any function positive with positive support, so in time. So this function vanish if time is negative, Euclidean time is negative. So this is what reflection positivity is for the two-point functions, Schwinger function. For higher Schwinger point functions is the extension of this property, which essentially has a multi-point function in both sides and larger Schwinger function here, always even. So what is the meaning of that? It can be derived from the principles I mentioned at the beginning. But a consequence of that is that you can recover the canonical formulation of the quantum theory, because you can now define the Hilbert space as the space expanded by these functions and the higher point generalization. And consider the product of this Hilbert space as this formula here. Since it's positive or non-negative definite, it will be a pre-Hilbert space. It means that the space you are constructing with these classical functions, these are classical, not quantum, only quantum is here. Then you have a linear space of functions where you have a product which is semi-definite positive. Well, it means that there is a huge kernel. It's not a Hilbert space. If you mod out this space by this kernel, you get a real Hilbert space. So complex, sorry, but a physical Hilbert space with a well-defined product. And that's it. So you have the Hamiltonian. The Poincaré representation here is nothing but the action of Poincaré in this space of classical functions. So what is time evolution? Just displacement of time in this space of function. And this is an operator in the space of this Hilbert space. So automatically you have a relativistic framework. And so you have not only for time translation, for any Poincaré transformation, and you can reconstruct the field operator just by looking at this action on this space of functions. So you can reconstruct the full quantum theory in the canonical formalism. Yes. There are some technicalities which are not necessary, is because this is derived from the principles, right? And sufficient, what I'm saying now, I can reconstruct the theory out of this data. No, in the higher derivative theory is not, because it fails. I will not show you why it fails. I will choose another alternative, which is simpler technically, but it can be done. In fact, we have done in a paper with Ilia and some other people for this theory. We have explicitly shown that it's not reflection positivity, just this two-point function. So what it means, reflection positivity in mathematical terms, that this, as considered as operator in the space of functions, is a positive operator. Why, the meaning of reflecting time is that since you are in the Euclidean formalism, when you go backwards in time, you have ut, u dagger t, okay? These two operators. One is the inverse of the other. In the normal Minkowskian approach, one is the inverse of the other. But when you have Euclidean time, there is no such taking the conjugation keeps the operator itself, because essentially in real time, H is alpha joint, so you have the same. So you cannot take the inverse on the left-hand side of the field. The only way of doing that is putting a reflection here. This is why the reflection is important in the Euclidean formalism. And it took 1 decade to find this property, till Osterwalder rather discovered in Harvard that this is the necessary condition to reconstruct the full theory. But the problem is that in this polynomial ghost, this property is not satisfied. So you cannot reconstruct the canonical formalism this way. So what happens if you have another kind of ghost? For instance, instead of having real zeros in the polynomial, you have complex zeros. Of course, they have to be conjugated because the whole polynomial is real. So you have a distribution of zeros of this type, okay? What happens there? Well, it's much harder to prove things, but first you have to try to make a weak rotation, then you have to find an appropriate path just to rotate and get analytic extension in the pure imaginary time. That's the Euclidean formulation. But it can be shown that the choice of the path it always involves a violation of Poincaré invariance. So it's not automatic that you can make the analytic extension. But in some cases, you can. Well, in that cases, again, positivity, reflection positivity is violated. This proof does not include all theories, but a large family of theories. So, but then, to escape this fate of polynomial ghosts, people invented what they are called transcendental non-local theories, or in other terms, ghost-free theories, right? An example of that is this theory, which is a generalization of the quadratic gravity formulated by Stell, but putting in a sandwich some exponential of the D'Alembertian with some parameter epsilon multiplying to a certain power n in the middle. So if you write this in momentum space, so the Fourier transform of the two-point function, you find that there are, apart from the physical zeros, there are no zeros associated to the exponential, because the exponential function doesn't vanish in finite points of the space. So there are no poles, then there are no ghosts, okay? But here the ghosts are hidden at infinity. So the transcendental functions, you know, all these pathologies appear at infinity. But it's true, there are no ghosts in the real space, not pathological ghosts in the real space. Well, there are some technical problems, which I skip. But the question is, being ghost-free is like being sugar-free. Does it mean that what is left is healthy? Are you sure? Well, that's the problem with ghosts. There are no ghosts in these transcendental functions, but maybe the theory is also insane, okay? So this is a question. And let's come back to the principles. Now I write it again in the same way, but I write some other implications. One is this Osterwalder-Radon reflection positivity, which I mentioned. And the other one is that, as was mentioned by Gabriel in his lectures, there should exist a Chern-Lehmann representation of the two-point function, at least the two-point function. And this has been discussed at the length in his Gabriel lectures, but let me just write it. Okay, it's here, so I don't need to write it. It means that the two-point functions, let me do it in the Euclidean formalism, okay? And this can be shown that is equivalent to prove reflection positivity, that the two-point function in Fourier transform can be written as an integral on a half line of this expression where rho is a positive density, okay? You have seen that. But then there is a theorem which was found long ago by Wither. In fact, he has a book completely devoted to this. The title of the book is Laplace Transform. Even if it doesn't look like a Laplace transform, it is a Laplace transform, right? And the book has a theorem which says this function here, the S to K, admits the decomposition of this form if and only if these algebraic expressions are matched. Very simple. So this is very practical. You can check. And this is why I will not discuss anymore reflection positivity, which is very involved, because you have here the formulas not easy to prove. But this one you can check. And in fact, we can check with few examples, and these transcendental cases. Let's first check for so let's take K of the two-point functions of P equal to 1 minus a polynomial here. P, let me put the leading order Pn plus many other terms, okay? Polynomial is like that. So if you take the first Wither identity, which I will prove, in fact, the first Wither identity, I can prove. So this is putting this inside. You can write it as so I can add here plus mu squared and subtract mu squared. So the final thing is the following. Okay? What I did is just add here plus and minus mu square. The first one cancels the denominator, the second one is written here. Now if you take the derivative, you can take the derivative, and what you find is the following. Is an immediate check. Which obviously is negative. You have a minus sign here, which is this. Oh, sorry. There is a minus sign here, but there is another minus which comes from taking the derivative in the denominator, and then everything gets positive, and this is the proof of the first Wheeler identity. So let's apply this identity, which is very easy to derive, to this polynomial thing. So what you have to do is multiply by p squared, and take here pn plus the rest, and take this derivative. Now I call it p instead of k. So this is derivative of the numerator is 1. Derivative of the denominator is p. So let me put an even number of powers. Square. So you complete putting here to get the common denominator. This minus this. Now you have a very simple expression, and you look at the leading term here. There is a competition between these two terms, because, sorry, here, when I take the derivative of the denominator, I didn't remove this p squared. I have p squared. So it means that here, I also have p squared. So these two terms are of the same order, 2n, p to 2n. So in the numerator, the leading term of the large p is of this form. Okay? Well, if n is larger than 1, this is negative. If n is 1, it's 0. And if n is smaller than 1, it's positive. So all the theories with n smaller than 1 are okay, but they are not local, because then this is not anymore a polynomial. Right? If n is negative, it's not a polynomial, or even if it's smaller. So for higher derivative theories with this n is larger than 1, so I mean, for instance, the quartic case, in the quartic case, n is equal to 2. Then you get that the wider identity is not satisfied, and because of the theorem, there is no Chern-Lehmann decomposition. This could be derived simpler, but if you apply the higher order criterion by wider, you will see that even at short distance, short piece, you have a problem with this ghost. Okay, here I have a summary of the same calculation. You can check yourself. In fact, they are contained in a paper of a few years ago with Ilya Shapiro and Leslie Rahar. That you apply to these transcendental kernels, which is much harder to do to show that they do not satisfy reflection positivity, is immediate following this type of calculation that they do not admit a Chern-Lehmann representation. So what to do? So we can even go to supernormalizable theories and even to transcendental supernormalizable theories, which include, apart from the standard quadratic terms of quadratic gravity, you have some kernels with the Lambertians. And in this case, also, you have that they do not admit a Chern-Lehmann representation. So it cannot be equivalent to the canonical formalism. But is there a way out? Well, there are many ways out. You have seen some of them in the Gabriel lecture, but let me just tell you one. Let me just consider one very particular theory, which is this one. I use some notation just to show, to make it very condensate. And some people in the audience complain, so I take advantage of that. I'm pretty sure that many of you also have the same problem. So I was writing at some point this formula. No, not this one, but something similar. So this formula means oops. This is the so it's just the normal product of Hilbert spaces for L2 functions. Okay? It's a condensate way of writing it. So, but now I add here a term which is, so by integrating by parts, this is the standard kinetic term of the scalar theories, free scalar theory. No mass. Let me just add a mass to this theory. So this theory is a higher derivative theory, and you apply the same criterion by wider, and you find that this does not admit a Chern-Lehmann representation, so we cannot go to the canonical formalism, and perhaps unitarity or some other principles are violated. But in this theory, you can do the following. Define a new field, which is given by this formula. And in terms of this field, the action excuse me, maybe let me put here 1/2, okay? Then good. So this theory now is very simple. It's a free field theory of a scalar field with a mass term. What I did is just reparametrization of the field. If we define the quantum theory as the theory which has a Hilbert space and whatever you have, as usual, for a massive particle, and you consider this operator as the fundamental field, there is no problem. It admits a Chern-Lehmann representation, everything. Well, this theory is consistent. It's the free field theory. What happens is that if you consider this as a fundamental field, the theory is pathological. And you see why. So, as I said in the first lecture, field theory is a Poincaré invariant quantum theory, Poincaré, where there is a representation of Poincaré algebra, which has a specific operator for one field, at least one. It can be more. I mean, you have vector theories or gravity. But you have to specify which field you are considering. For instance, these functions, which appear here in the reflection positivity, are correlation functions in the Euclidean space of the fundamental fields. If the field is 5, you have an S2. If the field is the capital 5, it's another one. And one of them is reflection positivity, the other not. One admits a Chern-Lehmann, the other not. So what is the problem with the pathological case? The problem with the pathological case is that if you compute this for the nice fields, this analysis, which I describing to you, was originally due to Andrei Slavnov, who passed away last year. He was very familiar with higher derivatives theories in Yang-Mills. He has even a book in collaboration with Faddeev, Ludwig Faddeev. And they have, Andrei Slavnov has a paper where he describes this. So this is 0. Perfect. Microcausality satisfies. This field does not satisfy microcausality. So what fails is microcausality. I think I agree with what you have done. But it's very simple to see, because you just replace in this formula this, and you pass the field 5 to the other side, which is non-local. And you try to compute this. This is a good exercise. In this lecture, I did not include exercise. This could be one. The other one will be to prove in this list of theories that the Wither identity is violated. And so this operator is equal to and does not satisfy this equality. So it's very simple to pass from one safe theory to another one. What is the difference between the two theories? If the theory is free, okay? So it's very easy to do it by hand. You have the vacuum. Then if you apply the field capital 5, you generate one particle state with mass, okay? If you apply 2 I's, you go to 2 particle states and perhaps to the vacuum too. A component is back in the vacuum. And so on. You generate the full spectrum of the theory just by acting on the vacuum many times with this field. Dressed with these functions, everything is well defined. These are the wave packets. So the theory is consistent. But what happens is that in the theory upstairs, you have many more states. Because between the vacuum and the first one particle state of this theory, there are the states of this guy acting on the vacuum. And so what in practice occurs is that you have a squeezed Jude-Hilbert space in the second theory. And in this space, the theory is consistent. And you never find the other states because you don't have this field in the theory. You can do it by hand, but it's not fundamental. So it's an operator which is acting there, but it's not fundamental. So that's the physical difference between the two approaches. So it might happen that in higher derivative theories, something similar can appear. There are some fields which are, in terms of which the theory is consistent. In particular, there are conjectures that if you have gauss which correspond to complex conjugate poles, they can form a condensate. The operator of this condensate have nice correlations. So the theory can be safe. So there are many ways of escaping this fate of not having a Chern-Lehmann decomposition. So the theory with higher derivatives can have problems at the classical level, the problems pointed out by Ostrogradsky. Although there are some models, like the one described in your first lecture for the Pi-Schulenbeck oscillator, which to some extent is a toy model of this. And in that model, it has been found by Bigman that there are many stable regions in phase space where you never see the, so maybe in this sector you have some stability, even at the classical level. So going to Euclidean from Lorentzian formulation, I have discussed this point, but it can be problematic, as I showed this rotation, some cases cannot be done. So there are theories. So this analytic continuation from Minkowski to Euclidean, in these theories, generically speaking, cannot be done. So it changed completely the framework. And the next conclusion is that gauss-free theories are not necessarily healthy, right? Like sugar. Or because these non-polynomial models also have troubles. Not ghosts, but they do not have reflection positivity or Chern-Lehmann decomposition. Well, this is the statement, and then there is a way out, which I will spend my last part of the presentation in another way of escaping this problem. The way is quite heterodox. It's just, you have to break one principle. Here we broke microcausality, right? But you can break any other. You can break Lorentz invariance. Why not? In principle, it seems to be sacred because it was created by Einstein. But I don't know if you are familiar with the fact that quantum chromodynamics, which is perhaps the only one quantum field theory in 4 dimensions, which is self-consistent, with the reduced set of principles, so not effective field theoretical approach. In those theories, most of the results we know are done in lattice numerical computations. Lattice case theories break Lorentz invariance because you discretize the, sorry? Sorry? In the formulation, in the computer, you are breaking Lorentz invariant. You recover in the continuum limit, but you start with a theory which is not Lorentz invariant. Okay? There are many ways because there is a relic symmetry, because you have discrete rotations you can keep, but yeah. But here, there are other ways of breaking Lorentz invariant that perhaps you restore Lorentz invariance in the infrared, like in QCD. And in particular, this way also can be done. So let me just mention how you can do that in a way that is quite safe and can be applied to quantum gravity. Let's first, as we did in all lectures, apply to a scalar field theory. So the idea is to modify the theory for the scalar, which was here, in a way that we include more space derivatives in the field, in the special part of the field, and time derivatives we keep second order. Because the fundamental problem of unitarity is that there is no theory which allows to have higher derivatives in time. The problem is to make higher derivatives in time. In a space, you can make as much derivatives you wish, and you will not lose unitarity. If unitarity is your first principle, then this is a legal proposal. Keep two derivatives in time. I mean, two because here is phi squared, but integrating by parts is two derivatives on the field, okay? Here you violate Lorentz because unless nu is equal to 1, this is not the standard term, right? Okay, you violate. Then you have a mass term, and you don't touch the interaction or mass terms. Well, you can now, all the dimension counting of the fields change because you have a different scale counting for the space-like coordinates and time-like. You put a nu here to accommodate the fact that everything here is scales correctly. You have that the phi field, the scalar field, has this dimensionality. So there is a parameter nu, which is the one which enters here. And according to that, you have this parameter lambda, which is in the standard relativistic invariant field, is dimensionless. Here is not. You have some dimension depending on nu, okay? Then this theory here is super renormalizable. I mean, you can check it by power counting because here are the countings, so you can do it without suffering by power counting. That in this case, 3 nu minus 1 larger than 0 is super normalizable. And in this extreme case, where this is 0, is renormalizable. In particular, the theory with n equal 1 is renormalizable because it's the standard theory, right? Nu equal 1 is the free, well, not the free, the self-interacting lambda phi 4, but this we know, perturbatively renormalized. Non-perturbative, nobody knows. Probably not. But n equal 2, so a bit bigger than the nu equal 1, the theory is super normalized, so very well. So only very few loops are divergent and the rest is finite. You have to renormalize just to a certain order of perturbation theory. The same thing can be done for gravity, and this has been done for Hoshaba, and suggests us the following. You remember the canonical formalism, because now since you are breaking Lorentz covariance, we have to come back to the first lecture, the canonical approach, where you split the Einstein action in terms of the extrinsic curvature tensor here and there. So this is the original action we have in terms of the lapse function and the shift function, okay? So here are hidden the other terms. So, so you have it here, right? But then, if you allow to have more terms in this part, just when you introduce the same breaking here, as we did in the scalar case, then it turns out that to find a renormalization prescription for this theory, you have to add these terms, which were not in the original Einstein equation. But this is space-like, you know? This is the Ricci, three-dimensional Ricci tensor. Here you still have the four-dimensional one, but you have here again Ricci square and some other contraction of Ricci cube and all this. If you add these terms to the Lagrangian, then the theory, Hoshaba, is renormalizable, okay? And you do not violate unitarity because you keep two derivatives in time. where are the two derivatives? Here. You know, what you did in this theory is to keep the terms where they have two derivatives in time, here in this part, right? And in the part which depends on space-like derivatives, you have higher derivative term. There you don't care. Okay? So you achieve in this way a theory of gravity which is renormalizable and which is unitary. The only problem is that it's not Poincare invariance in the standard sense. But the question is, can you recover that in the infrared? Formally speaking, yes, because these higher derivative terms in the infrared are not relevant. So formally, yes. But there are some problems. So let me just, for publicity, make a slightly different way of breaking Lorentz invariance we formulated with Pronow meter long ago, which is the opposite as Hoshaba. Hoshaba introduced higher derivatives in the here. This is for the scalar field, right? So Hoshaba introduced here in the special part higher derivatives here. But what we did is just in the kinetic term, we introduce space derivatives there. This keeps two derivatives in time, so it's not violating unitarity. In fact, this was applied as a regularization of Young-Mills theory. And you make the counting exactly. There are two regimes, one where the theory is supernormalizable, and the other one where is only the extreme one is renormalizable. Good. So gauge theories, which is the case where we formulate this theory. Again, you put more covariant derivatives in the kinetic part, so Coulomb electric field of Young-Mills. And so this keeps unitarity. In fact, classically, you can see that you have a Cauchy problem where the initial conditions depends only on the fields and first time derivatives of these fields, which is good, guarantees unitarity at the quantum level. And then you have, so you don't modify the, and in this theory, in this formulation, the advantage is that you don't have to include new terms to cancel the divergences. All the divergences can be absorbed just in this form, which is much simpler than Hoshaba. And again, you have two regimes, one when nu is larger than 1/2, or when this is just 1/2. In both cases, the theory, in one case is supernormalizable, in the other case is renormalizable. Gravity. Well, the same idea. You put higher space derivatives in the quadratic extrinsic curvature term, which contains time derivatives of the metric, but you do not increase the number of time derivatives, just two. So it's an ordinary, it's like Newton equation. So you have the left-hand side of the Newton equation is just acceleration. In the right-hand side, you have terms with higher derivatives, in this case of space-like coordinates. In mechanics, you can do nothing because there is only time. But here, you have a formulation which is quadratic in these extrinsic curvature terms, and nothing else. You don't add anything. By power counting, you could add many other things, but you don't need, because this is the minimal subtraction scheme which takes the theory renormalizable. So the theory, with very few terms, is renormalizable. So is good. But let me be not so optimistic. How we recover the Poincare invariance at the very end? Of course, in the renormalizable case, which is the most interesting one, there are running of the coupling constants. So many terms here have coefficients which are running. Okay? Especially in the Young-Mills case. In the Young-Mills case, the coupling constant is running. Even in this case, it's renormalizable or super-normalizable, but it's still running. It turns out that there are cases where this running, in the relativity case, means the running of the speed of light. Because the speed of light is the difference between the special part, the special derivative, and the time derivatives. So there is a running of speed of light, which is very interesting framework, because nobody thought about running of speed of light. You have a lot of parameters in field theory, but the speed of light is sacred. First of all, is nothing sacred, because if you believe the path integral approach to quantum gravity, you have to sum over all metrics. And some metrics have a speed of light, c. Some other metrics don't have c, have c prime. Not all metrics have the same speed of light. You don't fix that. So the only one which survives here in Minkowski space-time is Minkowski. But this just as a background metric magically appears, although in quantum gravity the formulation should be background independent, but in practice not. We have a condensation of this Minkowski metric locally. And in cosmology, you have even other more involved metrics, like Friedman metric. But if you have a running of the speed of light, I'm talking now not in gravity, in, for instance, Young-Mills. You should say, oh, either you go to infinity speed of light, which you will recover non-relativistic theories, or you go to zero, which is even more dramatic, okay? You have no... But this is not the case. There is an infrared cutoff, naturally, like in QED. In QED, you have the running of electric charge. And you have the Landau pole in the UV. But in the infrared, you don't have zero. There is a cutoff, which is the mass of the electron, which stops the running. So there is a cutoff in the infrared, which saves the running of the coupling constant. So in gravity, the same thing will happen in these theories. There is a stop of running of C in the infrared, and is fixed at some value, right? So you will get that the speed of light is frozen at some scale, which is the scale where we have the speed of light we see here. How far is this infrared from Planck mass? Well, this depends on the details of the theory. But this but, which is there, which is disappointing, is that if you have SU2 gauge theory, you can find an infrared cutoff where the speed of light is frozen, okay? And you recover full Poincare invariance. But I have SU3 do the same, and I have another speed of light. So the speed of light is depending on the theory you are quantizing. And this is very disappointing, because so far the speed of light is universal. All fields do have the same speed of light. And we don't know why, and we don't know this is what makes this scheme not self-consistent, because it explains one speed of light and one recovery. In all theories you recover, because for instance in SU2, even if the theory is conformal, in non-perturbative calculations you get a scale, is broken, the conformal invariance, you get the mass of the glue ball. And this is the infrared cutoff. After that, you have Lorentz invariant. But in SU3, you have a different cutoff, infrared cutoff. So a different mass gap. We don't know. But this is the only, in my opinion, the only drawback of this non-relativistic approach. And not only, is not the only, theoretically is the only, but also experimentally is that we don't have any signal of violating this Lorentz invariant. This plot is, I mean, a few years old plot. There is last year update of this graph, but what is kept is that what people measure here is that the time delays from very bright blazars in, I mean, very distant active nuclei in the universe. And they say that they receive two signals at different frequencies in the observatories, in gamma rays, essentially it's in gamma rays. And there is a time delay between the one which is more energetic and the one which is with low energy. And the claim is that if you have a violation of Lorentz, this implies that the dispersion relation is not the standard one, the quadratic one. So it's also higher derivative theory. And this will explain that depending on the frequency, you have a different delay. And so they use the data. Unfortunately, the delay is very low, and you assume, which is not clear, that they are emitted at the same time. If not, you are doing nothing, no? But let's assume that they are emitted at the same time. And you compute what will be the scale you need to introduce, because you are breaking Lorentz, to at which scale you have to break Lorentz to explain the data. And it turns out that the scale is much below the Planck scale. And in this, people wanted to explain this data as an observation of quantum gravity. Since the scale is much below, of course, these results are not associated to quantum gravity. And this is disappointing, but people still keep analyzing these kind of events. So this suggests that there is no breaking of Lorentz invariance and universality of the speed of light, which is against the Hochschild-Lipschitz and the other versions like the one by Mitter and myself. Okay, I will stop here, and I will be glad to answer your questions. Thank you. Yes. Not explicitly. It's in power counting. The formulation I present to you it was the original one by Hochschild. But some people found that he was using a gauge which is not justified. So some people modify slightly in the best way his approach, but they never check it because it's a tough problem. It's a very tough problem. To compute loops in quantum gravity, any version, including this one, which is more complicated than the covariant ones, is a tough thing. And you can do it with help of computers to a certain order, but you cannot. So it was based in power counting.
Yeah, but I imagine something like based on algebraic renormalization or something like this.
No. As far as I know, No, no, but this very, I mean, I'm aware of this work by Barbinsky, but I haven't read in detail the papers. But even in QED, the proof of remarkability took a long time. They were proven formally for few loops, but there were very subtle problems at 13 order of perturbation theory. Some subdivergences in diagrams which require modification of the renormalization prescription, starting from HEP, Volibov-Sirkov, and so on and so on. And the last one was given by Zimmerman. It took more than 13 years to fix it. So I don't know if this was done on the same foot as this proof in yeah. Yeah, the example, this example.
Yeah, but isn't that expected? Because you change the what you're copying?
No, one interesting thing, which I didn't remark, is that even if you break Lorentz, you keep gauge invariant exactly. But by gauge invariant, I mean covariant gauge invariant. So any gauge transformation which is space-time dependent, this symmetry is preserved. Which is amazing because you are breaking Lorentz and you think that then all other gauge, for instance, gauge symmetries should also split. And not, I mean, you have full gauge invariance, covariant gauge invariance. The terms behave in a different way, but from the gauge viewpoint. But this was not your question. I didn't answer. So can you repeat it?
Because you said that you have different velocities of light.
Yes.
When you come to different fields, right? SU3, SU2.
Yes.
But isn't that expected? Because you are copying with different fields.
Well, but it's expected, but I don't like it to have a different speed of light for each field.
Yeah, but like gravity couples with everything. So you should expect that when you do the calculation with everything, you would have just one. Or not?
But you have to know what would be that one scale for everything.
Yeah, but I thought that the problem was that the infrared.
Yeah.
When you couple to everything, you have only one infrared couple.
What would be that?
Why you have to couple it? But you should have just one, right? When you have the
No, because I mean, I know the calculation, there is a beta function, right? But the beta function changed from one theory to the other. So you claim that you have universal beta function, no? Including all interactions in 1C. This, to some extent, could be conceivable if you have unification of interactions. But if you have a mess of interactions, I don't see how you can have different, can you have a unique stop? Because the idea, like in QED, is the following. Then you have to fix this scale at the lowest energy possible. So what is the lightest particle in the universe? This is the one which fixes the stop. But, you know, we still have dark matter without knowing and so on. Why there is a scale which fixes everything. So, in fact, for me, it's disappointing that the theory depends on how many fields you have. Because we don't know never what is the ultimate theory of the. So maybe next year some new party action is discovered. Shall I have to change everything? Because one more, this is not a good situation. In QED is good because it's the electron mass. Because all other, for instance, neutrinos are not charged and so on, they are not affected by that. So the QED is the perfect theory where you understand. It's stable. 1/137, it doesn't change if you change standard model and so on. Okay, if you change dramatically, maybe, but so this value is fixed. and very happy with having this infrared cutoff. But for this running of C, it's like gravity, I told you. Gravity affects the whole thing. All field theories are affected by change of gravity theory. But to change the speed of light, depending on the matter content of the theory, is not. In fact, you should have, universal scale should be gravity itself. But Planck mass is very high, so it's not reasonable to stop C at that scale.
Well, in the first part of your lecture, you spoke about Euclidean analytic continuation and how in that case of quadratic gravity, you can't do it, right? You can come back to Minicourse. You can do analytic continuation, but you can't do it with Minicourse. But I see, like, since the 80s, people doing all sorts of quantum gravity calculations in Euclidean space, but I not always see how it translates back to four-dimensional curved space. So it usually can't translate back, right?
What is the common folklore on that is that these are two different theories of gravity. Euclidean gravity and normal gravity. So it's not expected to be the same theory.
Sorry.
No, there are fundamental points. I mean, Hawking did some work on that. But Hawking himself was worried about the fact that this will be not equivalent to the standard one. So I know some theories in the list I mentioned here. This transcendental is written in the slides. Here. This theory. N equal 1. You have a finite theory in the Euclidean and a divergent theory in the Minkowskian. You know, the box in Minkowskian has two signs. So this is a regularization in the Euclidean, because all high frequency are damped, but not in Minkowski. So they could not be equivalent. So there is no analytic continuation. It's very hard problem, the analytic continuation. It was proved in the early 60s for standard theories, and it's highly non-trivial. You have to use Poincaré invariance to extend the cones of analytic extension, then do another trick, and finally you reach the imaginary axis. But it's not automatic. So it's not just put it in the formula I and that's it. Yes, I know. And so people keep also doing non-perturbative approach to quantum gravity, right? Sure. Yes, the field theory is not well defined until you do not specify which are the fundamental fields. Because it might change. So this is a reparametrization of the fields. And in one parametrization, the theory is consistent, in the other not. Sorry? No, one loop still. But what I mean is just at tree level. So you have divergences. Yeah, the term in the action is divergent. So for large P. So it's not smoothed. The propagator does not improve its behavior in the cases which are there. No, and one loop is always divergent in this high derivatives theory. That's true. I mean, yeah, but I mean that in this case, even the higher loops are divergent because the propagator is not improving the situation. N equal to 1. No, but we have polynomial. But these are not polynomial, exponential. Okay. More questions? Yes? You were first. No, can you repeat the question because? In the infrared. No, I'm not saying that. I'm saying that if you modify in the UV general covariance, you still could recover in the infrared Lorentz invariance. This is what I said. Oh, no, very poor. So the conclusion is that in the assumptions of these people is that the metric, background metric of the traveling distance of these gamma rays, the metric is modified in a way that changes the dispersion relation of this propagation of these particles in a way that they have cubic terms in momentum or quartic terms and so on. And then if this modifies because in the standard relativity dispersion relation, everything is the same for all case, right? In those theories which higher polynomials not. So it can happen that the light in the UV propagates in a different way than light in the infrared, okay? And this depends on the scale of these cubic and quartic terms where they appear, because by dimensional counting they have different dimensions. You have to put let's say a dimensionful parameter in the thing, a mass, let's say. So they are putting bounds on this mass because they almost see nothing in this difference of time delay. So the mass they have to put is much lower than the Planck. So the original assumption that everything was due to quantum gravity should imply that this mass should be above the mass Planck, okay? Can you speak louder? Sorry. Maybe you use this. Because they are recording this, and maybe the question and the answers are, I don't know how to switch on, maybe here. Try. Oh, you can tell me, close.
Oh. Hi. Yeah, I believe that. Okay. So I was wondering if there is any construction, or is possible a construction to have a bracket that is like invariant under reparametrizations. Perhaps not that microcausality is too strong, so you can. I don't believe that it's possible to have like a reparametrization invariant bracket that holds microcausality, but perhaps but weaken microcausality, like putting some exponential factor in the instead of as pure zero or something like that. Is there any possible construction?
Well, I mean, I think that you were discussing this point too, no? Oh, no, he is claiming that perhaps instead of having microcausality in a strict sense equal to 0, to have some a small value which is beyond the observable detection.
No, actually, that is. Suppose in that example, the problem is that if I make a reparameterization of my fields, I will have two different, let's say, commutators, values for the commutator. One that it's compatible with what I expect in the free theory, and the other one is not come from a high derivative gravity. So the point was, if there was any possible construction to create a bracket operation that is invariant on the reparameterizations.
No.
Okay, so yeah, that's the straightforward answer, because microcausality is too strong. So the second point will be, okay, if that is impossible, can we change a little bit microcausality to have a, let's say, consistent construction of bracket invariant with reparameterization invariant bracket that is like consistent with this new notion of microcausality?
Since I say no to the first question,
No,
the
the
second
second.
one it should be no.
Okay.
No, it's impossible because I can always make a reparameterization with. Because there is no principle. That's why, even classically, you have a Poisson bracket instead of this.
Because I was thinking also in this Lieb-Robinson bounds that appears in systems of quantum mechanical systems, that you have your commutator is damped by an exponential factor. That is like a fuzzy microcausality. So, and those systems sometimes exhibit reparameterization invariance.
Let me be more specific. Even if you have a well-defined bracket and you perform a reparameterization which leaves this bracket invariant, a canonical coordinate transformation, quantum mechanics is not invariant under that.
Okay.
So, which is much stronger. So, even if you achieve some, what I claim is that you perform a generic change of variables in the phase space, it's impossible to have a bracket which is invariant under that. It's impossible because you can perform any arbitrary change of coordinates in phase space, and bracket should not be invariant unless it's a canonical transformation.
Okay, but you can mode all the transform. You can mode your space, but the canonical transformation, and you will have certain representatives, and that invariant bracket will be an invariant bracket of those representatives. So you can, it's like, again, you mode out of the diffeomorphisms, the reparameterization, sorry, and you get an invariant notion.
It's a different thing because you are thinking on diffeomorphism, which is acting on the base of the functions, on x, y. Okay? But here, reparameterization is in the target, in the 5.
Okay.
Yeah, it's linked to the coordinates because it's a box, which is differential operator. But in principle, they are different things. One is in the target, the other. So this is not connected with diffeomorphism invariant.
Okay.
This is just in a standard fixed Minkowskian space-time.
Okay.
Which is, by the way, this, I mean, I don't see here now the guy who asked me, but microcausality in quantum gravity is a problem because it's not invariant under diff. Because this space-like situation refers to Minkowski background. Yes. The causal structure is fixed. This is addressed in this last reference I gave by Aishan. This problem is a serious problem of quantum gravity. Yes. Yes, sure, sure. You can even reverse the sign of time. So this is.
My question perhaps is way more simpler. I'm thinking about what you guys are talking about. Could we kind of impose maybe some kind of average microcausality to this kind of structures?
The best idea for me is local microcausality. Because after all, observers cannot travel too far. So the notion of a server is a local notion. You cannot compare things with mates in the lab unless they are close to you. So with this local microcausality, which is connected with these cones, even if they fluctuate, this can be perhaps implemented here.
So a local average could be possible, maybe, like.
Yes.
Interesting.
But not global. I mean, global. Okay, any other question?
Well, so let me just make a historical remark. You guys were talking about renormalizability. And for QED, there is this theorem called BPH-Z theorem. And that is the theorem that guarantees that QED is renormalizable to all orders in perturbation theory. And there are these four guys who give the acronym, and it really took 13 years to get around all proofs correctly. So to prove renormalizability, you have to work hard, really.
Yeah, I agree. So there was a diagram, 13-order perturbation theory, which the original fathers missed until they organized by trees and so on with Zimmerman.
Zimmerman was the paper in the 70s.
Yes,
right?
was the last one.
It was the last one.
But then there was a recent formulation by mathematicians in terms of algebraic operators, which was equivalent. But I think for physicists, the standard all proved by physicists is still more popular than this one, which is very hard to understand, which was by Korn's school with Hof algebras and all this. But in principle, they achieved also a formal proof after many attempts. Some of them were failing as the physicists in the original one. And I don't know, since you asked about historical remarks, I don't know if the same kind of rigor was achieved for the standard model.
I don't think so.
It's a very nice piece of work what Toffen-Bellman did. There is a book which is called Diagrammer. Before knowing BRST, before knowing Slavnov-Taylor identities, they were able to prove that things were correct. And it's a lot of drawings, but it's self-consistent. But I don't know, they didn't go to the full approach where you can have subdivergences and trees and so on. I don't think nobody has done.
The approach that I mentioned, algebraic renormalization.
Crying.
So not algebraic TFT, but the one based on BRST. I think this has been done to the
For the standard model?
Yes. Using BRST? Yes. For example, there is a book by Silvio Sorella and Oliver Figuet, where they develop all this formula.
Mm-hmm.
But this is based on the BPH theory.
So it's an extension of BPH for the gauge theories.
Combining the BPH and basically putting gauge theories on top of BPH.
So your question before was about gravity. The same thing was down.
My question was about Lipschitz, because then you break one of the assumptions behind
Yes.
BPH.
In fact, in this Hoshaba-Lipschitz approach, the BRST was not used at all.
Another historical remark, the proof of the renormalizability by Veltman and Toft was actually a warm-up exercise to go to gravity case. And this warm-up exercise gave them the Nobel Prize. So,
and also make the starting of the fight between Bellman and Toft.
and yeah, that's a historical remark as well, their fight.
So gravity is guilty.
Yeah, great. But could give you a Nobel Prize.
No, but Toft wanted 2 Nobel Prizes. He wanted the one by asymptotic freedom. And he claimed that he couldn't do it because he was spending a lot of time doing gravity calculations.
More questions, guys?
You said a few times during your lectures that when you go to the canonical formulas, you immediately break Lorentz invariance, break Diffie-Hellman-Films covariance, something like that.
In apparent terms, at the very end, not, but you split time and coordinate. So
yeah, but you foliate, but then you build your foliation, your manifold in a Lorentz invariance manner, no? When you build your metric,
but then if you renormalize without paying attention to this, you might not any foliation keeps Lorentz invariance. You have to be very careful.
Okay, but since we live in a universe where apparently, at least in an effective level, Lorentz invariance appears, we should at least try to build...
No, there is a fundamental problem in that. There is one theorem, which is called the Haack theorem, which tells you if you have an infinite volume, which we assume that our universe, space-like volume, if you have 2 theories with different vacuum energy, they cannot live in the same Hilbert space. They are orthogonal. So the operators of one of them cannot see the other. In gravity, this happens. In this foliation of space-time, the metric here is not the same as if there is time evolution, for instance, in cosmology, it's not the same 1 second after. How do you compare the observables, the operators, and so on? Vacuum is different.
If you take the metric to be quantum something.
No. I'm talking about field theory in a background which is evolving in time.
Okay. The problems always appear before we go even to quantizing the background. If you try to quantize the matter...
This is related to a problem which was addressed by Schwinger, which is the dynamic Casimir effect. So also Hawking effect and Unruh effect. So if you have a metric which is evolving or changing, the vacuum is different, and what was the vacuum in one formulation is a thermal state in another one.
Yeah.
So infinite number of particles. So this is a...
That's tied with how we define our quantum states like with these equal time commutators, and all our probabilities have to be defined in a time slice everywhere, in infinity. It's kind of crazy that we try to do that, like to define a vacuum for all space ever.
No, you can only do that if you are asymptotically Minkowskian.
Yeah.
For other kind of metrics, you cannot do it. For instance, the sitter, there is a problem in defining the vacuum in the sitter, as you well know. And the reason is just this. So it's another problem, but it's not quantum gravity, but it's also a problem which affects field theory in gravitational backgrounds which evolve in time. So if no more questions, let's go for lunch.
Yeah, let's thank Manuel for his great series of lectures.